clicker? Of course you do. Forget it. All right, just a quick recap. What is that? That is a capillary, a fenestrated capillary. And, come on. What's that? And what's that? Very good. Now, here's your first clicker question.
I gotta get mine out. Hang on, I just moved my seat. Don't start it.
Oh, geez. Well, I won't end it.
Don't end it without me.
All right. So some of the least permeable capillaries are found in the what, while some of the most permeable capillaries are found in the who. Is that it? 33? Oh. No. $36? Everybody click? Those who have them clicked should rephrase the question. So 36 is our number? All right, what's the answer? The answer is D. So D is the answer. So the least permeable, the ones that are going to be very selective about what they let in and out, would that be the bone marrow? Intestines? We want a lot of stuff to come in, right? Kidneys? Filtering system, so yeah, a lot of stuff goes through there. The brain is definitely not the least for by any means. So, all right. So remember where exchange takes place in the capillary beds. What do we call that area? The true capillaries. So that's where we start to see the red turn to gray and then eventually to blue as they feed into the venous portion of the system. So, here's another clicker question for you. Of the following vessel types, which are responsible for exchange of gases and nutrients with tissues? Five, 4, 3, 2. What was our number? 36. Click, everybody, click. All right, we're done. What's the answer? C. C. Remember, capillaries is where we have most of the exchange. All right, so when we look at where blood hangs out most of its time, or most of the blood volume, where do we see most of the blood volume? In the veins and the venules. What's a venule? So vein, venule, yep. So capillaries about 5%, heart about 8%, systemic arteries and arterioles 15%, 12% going to pick up oxygen, drop off carbon dioxide in the pulmonary circulation. So only 5% of your blood volume at any given time is going through the whole exchange thing. So, oh, another clicker question. Of the following cardiovascular components, which contains the majority of the body's blood volume at any one time? Five. Oh, there's 36. What's the answer? You better get this right. No! C. Not in the heart. You know these count. Yeah. Yes, they do. What's this? That's a problem. Because of what? Plaque buildup. What's it called? Not arterial sclerosis. Atherosclerosis. Which of the following vessel types, which conduct blood towards the heart, regardless of oxygen content? So which vessels bring blood where? Back to the heart. Five, 4, 3, 2. Ooh, a 37 now. Yeah, check your batteries. Make sure the light's going on when you click. What's the answer? The answer is D. Veins. Arteries carry blood what? Away from the heart. So, we sort of ended here last class, talking about pressure in the system. And this is the physiology of circulation. So we already know we have a pump, yes? And the pump is there to do what? Push blood through what? Yeah, the veins and arteries of the cardiovascular system, delivery system. That's what blood is. So with respect to delivery, wait a minute. Let's get a pen on here. So the delivery system then, the arteries and veins have to bring blood to the tissues for exchange. And blood flow is the movement of blood through these arteries and veins. What is blood pressure? The measurement of the force flowing through those arteries and veins being pushed by the heart pump. And what's resistance? As things move across the surface, they're going to be slowed down by, friction or resistance. So they're sort of opposition of flow, slowing things down. What would move faster, you with ice skates on the lake or you with ice skates on the road? Yeah, hopefully if the lake is frozen, that usually is quite helpful for the whole ice skating process. So you on ice, less what? And less resistance. So lots of resistance and friction. Yes, you're not going anywhere. So some of the things that are going to affect resistance in the system are things like blood viscosity. What if blood is too thick? It's going to slow down flow. It's going to increase resistance. How about blood vessel length? If I have a longer way to travel, there's more what? More resistance. It's going to take me longer to make a circuit. And how about blood vessel diameter? And think about movement. Think about my garden hose. Yeah. Yeah, you can push it further though, right? Because you still have the pressure behind it. So, all of these things are going to affect how fast blood moves through the circulatory system. So they also then talk about the relationship between flow, pressure, and resistance. That is a calculation. All of these things play a role in how quickly blood moves through the circulatory system. Am I going to make you memorize this calculation? No. 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 But they all play a role in moving blood through the system. And that's what you need to understand about all of these different factors. So blood pressure in the system, or systemic blood pressure, is going to play a big role in exchange at the tissue level, at those capillary beds. And arterial blood pressure is higher than venous blood pressure. Why? Arteries are doing what? They're leaving the heart where they just got a what? Where they just got a great big push. As they travel through the system, and this is a graph of what happens to the pressure as they travel through the system. What happens to pressure in the system once it reaches its total circuit and dumps back into the heart in the vena cava? It bottoms out. It's almost zero. So it's going to have 0 millimeters of mercury, which is how we measure pressure. When you look at barometric pressure, when you look at blood pressure, it's all measured in millimeters of mercury. By the time we go through the whole circuit that we've just discussed and hit the vena cava, which dumps back into where? The who? The right atrium, not the aorta. The aorta is way over there. That leaves the who? Left ventricle. I guess you got to look that one over. Yes? That's the highest pressure in the system. That's the big push to the system, right? So why is that pressure going like that? Yeah, because remember, I'm pushing and then I'm relaxing, and I'm pushing and I'm relaxing during the cardiac cycle. So we can actually measure the highest pressure in the system. What do we call that? The pressure of contraction, systolic pressure, versus the pressure, there's still pressure there, related to what? Or what is it related to? Relaxation of those ventricles, diastolic. So we can actually measure systolic and diastolic in, where do you measure blood pressure? In the arteries. Somebody was kind enough to use the proper region. What region is this? Brachial arteries, and we'll do that in lab. I highly suggest that you go and use your interactive physiology. There's a section in there on how to measure blood pressure. So if you don't know what that is, and you're not quite sure how to do that, who's never taken a blood pressure before? Oh, all of you have? Ooh.
Every day.
Every day. So what is it? What are you measuring? How do you physically do that? You listen. Can I hear blood flowing through an artery? Absolutely not. No. But if I take that blood pressure cuff and I apply a pressure to the artery and I do what to it? Shrink it down, and the blood is still going to come in at that pressure. And it's going to start to bang up against the sides of that artery. That's what you hear when you put that cuff on. That's called the sounds of Korotkov. Korotkov. You'll see it in your lab book. And then I'm going to close it off altogether. So now I don't hear what? Now I don't hear anything. And when I slowly release the pressure, the minute I hear bang, 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 that's going to represent about the highest pressure in the system, systolic pressure. And I'm going to keep releasing the pressure until what? You can't hear anything anymore. What's that represent? The lowest pressure in the system. Because you can't hear anything anymore when it's nice and wide open and moving nice and smooth through the vessel. So we'll do that in lab, but that's what you're measuring when you take a blood pressure. The highest pressure and the lowest pressure in the system. Again, we need to bring up our calculators for this test. So the mean arterial pressure of a person with a systolic blood pressure of 120 and a diastolic pressure of 80, and if we look on page 708 in our textbook, we see how to calculate the mean arterial pressure. So MAP equals what? 705 would be diastolic. Where am I? Oh, no, I'm trying to find my pen. Diastolic plus, what's a pulse pressure? How do you figure that out? Yeah, pulse pressure is another calculation you need to know. Equals what? Systolic minus diastolic. I'm running out of screen. Systolic minus diastolic is your pulse pressure. So back to the calculation would be pulse pressure divided by what? Divided by 3 equals mean arterial pressure. So in this calculation, 80 is the diastolic pressure, 40, and how did I figure that out? Yep, 120 minus 80, and that's kind of the average. When we talk about blood pressure, we see that number 120 over 80 is sort of the average blood pressure, and that would be the mean arterial pressure for the system. So that's sort of the line that runs through the middle of those guys on our graph. So you should know how to calculate the mean arterial pressure. You should know how to calculate the pulse pressure. And all of these pressures are extremely important for moving blood through these blood vessels. By the time we reach the capillaries, blood pressure has gone way, way down. But there's still a little bit left there, about 30, 35-ish millimeters of mercury left by the time we hit the capillary beds. And that capillary pressure is important for exchange of nutrients and wastes and fluids across the true capillary beds. What if the pressure starts to go too high in the system? Exchange can happen, but think about pressure pushing things. If the pressure inside the tubes is too high, what am I going to tend to do? Push too much what? Push too much stuff out of where? Where the exchange takes place. In the capillary beds. If the pressure is way higher than 35-ish, I'm going to be pushing way too much out. How about stuff being able to get back in? If they have to overcome too high a pressure, I'm going to have trouble getting rid of waste products because they actually have to move in at the capillary beds, especially respiratory gases. So those pressures are extremely important in exchange of nutrients and waste. Venous pressure is going to go way, way down. So how do I get blood back If my pressure is way, way down, now in my closed circuit, I have to get everybody back to the heart. So what happens when I have such a low pressure in the venous system? It's going to take a little while for me to get back to the heart, and that's why most of the blood hangs out there. But how am I going to help get that blood back to the heart? Yeah, muscles in different areas. So they talk a little bit about what we call the muscular pump. Muscles contracting, and this happens every time you breathe in and out. We talked about this last class. You're going to push against some of the major veins that are bringing blood back from systemic circulation for another push in the heart. So it's very, very important that these muscles contract to help the muscular pump. And they also talk about the respiratory pump, again, muscles pushing against these major vessels to push blood back to the heart. Why do we need the muscular pump and the respiratory pump help? Because of the pressure in the system. Pressure's too low. Okay, what effect does a long period of skeletal muscle inactivity have on blood flow? So if they're not moving, they're not pumping, they're just sitting there doing nothing. Think about the tubes, low pressure. What might happen? Five, 4, 3, 2, 37, 1. What's the answer? The answer is A. So blood would sort of pool up, slow in places, not having a help from the muscular pump. So the muscular pump is important for the venous system to get blood moving back to the heart because of the low pressure in the system. So we already know what cardiac output is, right? And if you forget the calculation, it's there. You're going to have to calculate that? Yes, you are. So I'm going to give you your test, your next test. Also will include the respiratory system. So I'm going to give you a little patient profile, which will include all of the information you're going to need to make these calculations on your exam. So in this instance, what information will I have to give you if I ask you to calculate cardiac output? I'll have to tell you what the patient's stroke volume is. I'll have to tell you what the patient's heart rate is, right? If I ask you to calculate mean arterial pressure, what information do you need? Yeah, the pressure, systolic over diastolic. But you remember, you have to remember how to calculate what? The pulse pressure. I don't have to give you that, do I? No, because you have all the information you need to do that. So that's what there's going to be a series of questions which will include the respiratory system. There'll be information in there in that patient profile that you'll need to calculate certain things in the respiratory system too. So calculator, no cell phone, calculator, the old-fashioned add, subtract, multiply, and divide calculator. Okay? So I'm giving you fair warning. The next exam, you're going to need a calculator. It doesn't have to be anything fancy schmancy. It just has to add, subtract, multiply, and divide. If you can do that in your own head, which many of you hopefully can do, you don't even need a calculator. But if you feel the need for that support, that's what you need to bring with you. Okay? So, in order to maintain blood pressure, the central nervous system is constantly monitoring pressure in the system. Does anybody remember what kind of receptors, think back to last semester, from the nervous system monitored pressure? They're a type of mechanoreceptor. They're called baroreceptors. And we're going to find them in different places throughout the body. There's a group of them located right near the pump. And those baroreceptors are constantly monitoring pressure in the system. So, if I need to increase or decrease pressure in the system, I have to act in certain ways to do that. This diagram is going to show us some of the different things that we can do to the tubes and the pump to increase or decrease pressure in the system. So when I exercise, I'm going to increase the respiratory pump. If I increase the respiratory pump, what am I going to increase in the system? Pressure in the system, right? That is going to speed up because my muscles are moving more. They're pumping against the tubes more. That's going to increase venous return. And that's going to increase EDV. What's EDV? End, ED, diastolic volume. Remember my favorite diagram in the whole world? There was an EDV in there. So the volume after diastole is end diastolic volume. That in turn is going to increase the stroke volume. When I increase the stroke volume, I increase what? Cardiac output. Sympathetic nervous system activity is also going to help increase cardiac output. Epinephrine in the blood is going to cause what to happen more forcefully? Contractility of the cells. So epinephrine, remember we saw that near the beginning? That little second messenger system that you all were keen on picking out? Yes? Okay. Increase contractility. Decrease end systolic volume. What's systole? Contraction. It's going to decrease it because it's going to cause what to happen when contraction happens? Contraction of the muscles more forcefully pushing more out after systole. That's going to increase stroke volume as well, and then in turn increase cardiac output. Yes? Parasympathetic division of the autonomic nervous system is, what's that doing for me? Slowing things down. Okay? So if I slow down heart rate, what am I going to do to cardiac output? Decrease it. If I speed up, and this is kind of confusing, this diagram, because it implies that decreased activity is going to increase heart rate, but it doesn't. It does the opposite. So sympathetic activity is going to increase heart rate. Parasympathetic activity is going to decrease heart rate. And again, if I increase heart rate in the calculation, I'm going to increase what? Cardiac output. If I decrease heart rate in the calculation, I'm going to decrease cardiac output. Okay? So everybody understand how blood pressure is maintained. So the short-term mechanisms, the nervous system, an area called the vasomotor center in your central nervous system. And where do I find these brain centers? Think middle. Those middle brain regions are what's going to help you control heart rate and respiratory rate. We call that the lower functions. And think about where they are. They're really, really protected, aren't they? Those lower brain regions. That's probably a good design, isn't it? Because we know it's important that you constantly be breathing and constantly have a heartbeat. So they're very protected by all the other brain regions. So in the central brain regions, of course my favorite word in the whole brain, the medulla oblongata, is where we might find some of these centers. And again, these are going to help control the rate of heartbeat. And they are going to get information from baroreceptors, pressure receptors, to let them know how strong or how weak the pressure is in the system. So if we look at this little negative feedback mechanism, everybody picked that up right away, right? Constantly trying to maintain pressure in the system. Again, pressure in the system is key for exchange in the system. If the pressure's too high, too much exchange. If the pressure's too low, not enough exchange. So we're constantly trying to maintain pressure in the system at normal range. So we see two sides to this diagram. Stimulus, in this case, for this negative feedback mechanism, is an increase in pressure in the system. When an increase in pressure occurs, the first groups of cells, those baroreceptors, and where's the carotid sinus? Some major vessels that are what? Going to supply blood to who? The brain. Oh, that's a good place for them because the brain's kind of communicating with everybody, right? And also we find some in the aortic arch. Where's the aortic arch? Yeah, in the aorta as we leave the heart. So there's a nice group of receptors because that's my first indication that pressure might be increasing in the system. They're going to communicate, those baroreceptors, with centers in the brain, those central brain regions, and they are going to, in the case of increased pressure in the system, try to do what? Decrease pressure in the system. So one of the things I can do to help decrease pressure in the system is I can actually cause the blood vessels to do what? To dilate. That's one quick thing I can do, because when they're squished tight, the pressure in the system is higher. So vasodilation can happen, and that can happen pretty quickly. What else? Yeah, kind of slow up that heartbeat, slow up heart rate. Who might I signal to do that? Who's in charge of keeping the rhythm? The autorhythmic cells, that's sinoatrial node, atrioventricular node, the conduction system of the heart. So decrease cardiac output, decrease RR. What's R? What's R? Didn't we say something else? Resistance! Return blood pressure back to homeostatic range. Now, what if blood pressure goes down? How can I quickly increase pressure in the system? Yeah, I can do the opposite. So decreased blood pressure, arterial blood flow falls below normal range. Again, those baroreceptors are going to be our first line of communication. They're going to let the brain know that, oops, pressure's diving, quick, do something. So what's going to happen? If I can increase contractility, I can push out more volume. If I can push out more volume, I can increase pressure in the system, right? What can I do to my blood vessels to quick increase pressure? Constrict them. So when I constrict, I increase resistance, I increase pressure in the system, increase pressure in the system, bringing it back to homeostatic balance. Yes? We're not only going to communicate with the heart and the blood vessels to increase and decrease pressure. When we discuss the renal system, we're going to see its role in regulating blood pressure. What do you think the renal system's doing for me? Hold that thought. Answer this question. Predict the change in peripheral resistance as blood vessel diameter increases. 5, 4, 3, 2. What's the answer? The answer is A. So remember, as the blood vessel diameter increases, what happens to resistance? It decreases. If the blood vessel diameter decreases, resistance increases. Okay, so think of what the words mean. So the answer is A. So some of the things that are going to help affect blood pressure, and we can see this table for us on page 709 in your textbook. We see that different hormones can control blood pressure by increasing certain effects. And we see up there, besides the heart and the arterioles, who else is on the list? The kidneys, kidney tubules, kidney tubules, kidney tubules. So now I repeat my question. What's the kidney have to do with blood pressure? Volume, exactly. A really quick way for me to increase pressure in the system is to add more water back into it. And the kidney's job is to filter wastes from blood plasma. But another major role of the kidney is to also maintain water balance. So when you make excess water, and a whole bunch of reactions of metabolism do that, and when you drink a lot of water and you eat foods with water in it, you're going to absorb that water into the circulatory system. It's the kidney's job, along with all the other things it does for a living, to maintain water balance. Too much water in the system is going to do what to the pressure in the system? Increase it. Not enough water in the system is going to do what? Decrease pressure in the system, right? So a real quick way that I can also affect blood pressure in the system is to help the kidneys, have the kidneys help me. And again, we'll talk about these guys in more detail when we talk about the renal system, but the renal system is also a very important part of maintaining proper blood pressure. So we have chemoreceptors, we have baroreceptors. They are going to help us maintain pressure in the system. So we have different hormones, again from that list above, that are going to help affect water in the system, that are going to in turn affect pressure in the system. This is something called the Renin-Angiotensin Pathway. And we already know what these hormones do, right? Or at least we should, because we just had a test on it. Yes? So you've heard these guys before. Are they ringing a bell? Yep. So, baroreceptors, again, are going to detect, in this case, decreased pressure in the system. So what do I have to do before you even look at anything on this diagram? When the pressure goes down in the system, what do I have to do? Bring it back up. If we're talking about the kidneys, what can it do to help? Add more water back into the circulatory system. So when we look at this pathway, we see sympathetic stimulation is going to promote a series of hormones to be released. Those hormones are going to affect water reabsorption. When we talk about the kidneys, we'll see they're like little filters, those kidneys. There's little units in there called nephrons. And your blood volume is going to be filtered many times throughout the day. Get rid of wastes, get rid of excess water. And how the kidneys work, it's kind of a little backwards, but all the blood comes into these little filtering units, and then we suck out as much fluid as we possibly can. Well, inside that fluid is a lot of good things that we really shouldn't have sucked out. So then we have to reabsorb before we let that blood volume go back into circulation. We have to bring back into the circulatory system the things we really shouldn't have sucked out. That's called reabsorption. And in order to get water to be reabsorbed, and water's kind of a follower, it follows charged particles. Which charged particle might it like to follow? Sodium. So if these cells, instead of letting free more sodium, when they get a signal from the Renin-Angiotensin Pathway, and this guy called aldosterone from the adrenal cortex, if they are told reabsorb more sodium back into the circulatory system, who's going to follow? Water. This is called obligatory water reabsorption. And this series of release of hormones is going to cause those nephrons, those cells, to reabsorb more water back into the system. It does it by causing it to reabsorb more sodium back into the system. Water's going to follow. That's going to result in what? An increase in blood volume. An increase in blood volume is going to do what? Increase pressure. The other thing we can do is what? Because we need to increase pressure, remember? Yep. So angiotensin has a secondary effect. It's also going to cause vasoconstriction as well. Combination of the two is going to do what to the pressure in the system? Increase it. Yes? These are really good diagrams, though. I know you're like, oh my God. But if you can talk your way through these things, you'll understand the concept. So use the pictures to your advantage. I'm one of those people that likes the pictures, if you haven't figured it out yet. Me and my diagrams. Damn, there she goes with another diagram. But talk your way through them. If you can see it, maybe that'll help you understand the concept. So here, what's happening? Oh, a lot of things are happening. By the way, short-term mechanism and hormonal control is written for you on page 709. And that diagram we just went over is very helpful to understand that. So factors causing an increase in MAP. What's MAP? Mean arterial pressure. So what's happening here again? If I need to increase pressure in the system, that means pressure starting to go down. So all of these wonderful things are going to help increase mean arterial pressure in the system. And these are some of the reasons why pressure might be going down in the system. Things like dehydration, a high hematocrit, not enough what in the system? Fluid, right? Because remember, what is your blood volume mostly? 55% is plasma. Most of plasma is water. So when you become dehydrated, it affects pressure in the system. Your body size is also going to affect pressure in the system because you have an increase in what? Blood vessel length. And because of that, your body is going to try to compensate and do what? Increase pressure in the system. Sometimes it overcompensates a bit, and you can end up with high pressure in the system. So all of these, crisis, stressors, exercise, trauma, increase in body temperature, is going to cause effects chemically in your body. And not only baroreceptors are going to monitor pressure in the system, but who else is going to help me monitor pressure in the system? Those chemoreceptors, chemical changes. When I have a decrease in pH, a decrease in oxygen, what do I need to do? Think of the decrease in oxygen first. Don't worry about the pH, because that might confuse you. If I have a decrease in oxygen, what do I need to do? Get more oxygen from who? The lungs. When I have a decrease in oxygen, I have an increase in carbon dioxide. And the balance of these two, believe it or not, are going to determine my blood pH. So chemoreceptors are constantly monitoring that to help regulate blood pressure in the system. Are you with me? I know this is confusing. But pressure in the system is extremely important. So how do I monitor pressure in the system? Well, I can take a pulse, and that can sort of give me what information? When I take your pulse, what information does that give me? Heart rate. And remember, that's an important number I need to know so I can figure out what? Cardiac output. So heart rate is important. And I can measure heart rate without any instruments. All I need is what? My fingers. And what is a pulse? It represents, but what is a pulse? Physically, what is a pulse? It's a pressure wave. Push from the ventricle. Wave of pressure. And the best place to feel a pulse is where? In an artery, right? Can I feel a pulse wave in a vein? Let me go back to this. Can I feel a pulse wave in a vein? So where am I going to feel them? In these guys, right? In that region. So anybody here, and it's kind of hard for me to stick my hand in your chest and feel a wave of pulse in your aorta, because that might hurt a little bit. Yeah, don't do that. The patients might get a little grumpy if you try to do that. So there's certain places in my body where those arteries kind of hang out close to the surface. And those are the best places to feel that pulse wave. A, it's got to be in an artery, and B, it's got to be close to what? Closer to the surface. So we see we can feel certain pulse pressure, pulse waves. That pressure wave can be felt in several different places, and that's what a pulse is. So guess what you're going to be doing in lab? Measuring pulses. And we won't make you do the femoral artery. That one's a little embarrassing. So that's what a pulse is. A pulse is a measurement of pressure wave. In order to measure the pressure in the system, what do we have to do? Can we just go, oh, yeah, that feels very strong? We have to measure. That's only going to give me information about heart rate, right? What else do we have? What other things can we do to measure pressure in the system? We measure blood pressure with a blood pressure cuff. So, auscultation or osculatory methods, that's a fancy way of saying blood pressure. We use a cuff pressure that applies a pressure to close off a vessel. What's that thing called? It's a sphygmomanometer. And that's the fancy name for a blood pressure cuff. That's right. So this is going to help me hear what's going on in those blood vessels. I can't take a pressure in the system by just listening, right? I have to apply a pressure to the system and then release the pressure. And as I explained before, the sounds of Korotkov, and those are described under measuring blood pressure in your text, are there as well. So, if there's too much pressure in the system or not enough pressure in the system, it's going to affect exchange at the capillary level. So, alterations in blood pressure are discussed in your textbook. What's hypotension? Hypo means not enough, right? Remember when we learned the terms way back when we were talking about tonicity? The hypo means the same thing here. So hypotension is not enough pressure in the system. Any systolic pressure below 100 millimeters of mercury. I'm not getting enough pressure to get exchange. So when your blood pressure takes a dive, what might happen to you? You might take a dive too. How come? Exactly. There's not enough pressure to push enough oxygen out. Not healthy at all for any patient.
There's a lot of dialysis patients that have blood pressures that
Yeah, yeah. And why do you think that might be? See, bing, 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 you're getting it. When you go to dialysis, what do? They remove a lot of the wastes, and they do that on a machine rather than your kidneys, which don't work the way they should. And many times it takes a little while for your patients to get back to equilibrium. Oh, well, then, yeah, then they have a problem. And if they're going to dialysis, what do they have a problem with? Their kidneys. And remember, that's one of the major players in regulating water balance. So if they have a problem because they have to go to dialysis, then it's probably most likely 100%. I'm saying 99.9% it's kidney issues. All right. So understand the difference between hypotension, not enough pressure in the system, versus hypertension, too high. Okay? If the pressure is too high, what are we going to do? Push out too much volume, including fluids. You're going to push out too much fluids. And people with chronic hypertension, one of the things you might find in your patients, especially their extremities, is what? Edema, swelling. How come? They're pushing too much fluid out of the circulatory system, and it's really hard because of the pressure gradient to get that fluid back into the circulatory system. It's hard for the lymphatic system to keep up. So you're going to get pooling fluid, especially in the extremities furthest away from the pump. So they talk about some of these imbalances. Chronic hypertension can lead to what? Heart disease. Remember, I stress the pump out too much. I'm going to wear it out faster, right? Can be hereditary. It can run in families. Dietary factors can also influence pressure in the system. Remember our friend sodium? Yes? Too much sodium in the system. Who's going to follow it? Water. So dietary ions can also affect pressure in the system. When the length of the blood vessels start to get too long because maybe you've been creating some extra cells that need feeding. Yes? Can that create problems with pressure in the system? Yes, it can. So obesity can also lead to problems with blood pressure. Age. The pump and the tubes are getting older. So age can also be a factor in affecting blood pressure. Diabetes. What the heck does that have to do with anything? What is diabetes? Diabetes mellitus, diabetes in general. Too much what? No insulin. Don't think insulin. Too much glucose floating around for whatever reason. Maybe not enough insulin. Maybe I start to make my insulin wrong. Maybe the receptors on my cells are the wrong shape. Any of those reasons can lead to diabetes. If I have too much glucose in the system, I have to regulate. Too much is going to make who work overtime? Kidneys. Yes? Kidneys have to regulate that. They have to get rid of the excess. And what are they also going to get rid of? Excess in turn, because they're trying to get rid of excess glucose. And they don't really mean to do this, but that's what happens. Anybody know what happens to a patient with diabetes mellitus? What's one of the symptoms? They pee a lot. They pee a lot. Is that going to affect pressure in the system? Yes, it is. Smoking. Who's our smokers? Raise your hands. No, they don't. They're afraid. They're afraid. All right. Well, smoking. Nicotine enhances the sympathetic nervous system and is a vasoconstrictor, which does what to pressure in the system? Increases pressure in the system. In my nutrition class, I have a very healthy 25-year-old male, yes, who is a fanatic about exercising and eating right, and smokes. And guess what? He's 25. He's got high blood pressure. Hello? So, careful. Smoking I already gave you my disgusting smoking talk last semester. I'll throw one in again when we hit the respiratory system. It's an expensive habit, isn't it? Just in cost alone. Stop smoking. Save your money. Take me to the Bahamas. In appreciation for me causing you to stop smoking. I keep waiting. Nobody is yet to take me to the Bahamas, but I keep trying. I'll go, hey, it's warm and there's pina coladas there. I'm on it. Pineapple. Oh, okay, don't kill me now. All right, so all of these things, all of these factors, remember, we're a fine balance. We're a fine chemical balance. And all of these systems are working together to help maintain balance. So understand the difference between high and low blood pressure and some of the risk factors associated with it. Blood flow through body tissues or tissue perfusion. If you look at this diagram, we see that the distribution of blood at any given time through the body is about as follows. So this is what? And I'm just hanging around eating Twinkies, watching SpongeBob, right? So, well, no, probably not eating Twinkies. Other parts of the body, about 600 mils. Abdomen, abdominal region. Why is there so much blood around there? If I'm eating Twinkies and watching SpongeBob. Yeah. Blood has to pick up all that wonderful stuff in the abdominal pelvic region, small intestine. When we dissect our pigs, you're going to see how highly vascular the membranes are that hold together the small intestine. Tons and tons of blood vessels there to absorb what's going on there. Kidneys, a lot of blood there too because I'm constantly filtering my blood volume. Skin. Yeah, there's a lot to feed. So 500. Skeletal muscle. A lot going on there. I need a lot of blood to the skeletal muscle. And what do I need a lot of? I got to make a lot of ATP. Yeah, I need the nutrients so I can undergo cellular respiration. What else is going to help me make a lot of ATP? Oxygen, yes? So all of those things are constantly being delivered to those muscles so I can make enough energy to move them. Of course, the heart would be nice if that could beat at all times. So that has quite the volume. And look at that brain. It's not that big compared to everybody else, but it gets 750 mils of that average 5,800 mil volume. Why? Yeah, it's kind of controlling the whole world there, right? So we want to make sure that we get enough of the nutrients and respiratory gases to the central nervous system, the brain, the spinal cord, so it can do its thing. When we change what we're doing, like strenuous exercise, we're going to move more volume at a faster pace. So this is blood flow at rest. That is moving through the pump, basically. And what are we going to do when we exercise strenuously? What's going to happen to that skeletal muscle value? It's going to increase quite a bit. Again, we're moving our muscles. We need to get more of the nutrients, glucose, oxygen, to those skeletal muscles for use. Skin, why does skin get more? Yeah, when you move your muscles more, you create more what? Heat. What's one way to get rid of excess heat? You sweat. And when you sweat, what's going on? I get red when I exercise. Why do I get red? More blood vessels are moving what? To the surface and doing what? Dilating, so I can release more of that excess heat. So we're going to see more of that blood volume in the skin at those times as well. When I'm moving around really quick, what happens to the blood flow in the abdominal pelvic region? Whew. I have other places I have to service. That's why they tell you, what'd your mother yell at you or father yell at you? Don't go swimming after you eat. How come? Yeah, because you might have trouble with the whole blood flow situation to a place that's going to need a little extra blood flow to digest your food, and you might get some cramps. So, blood flow through the tissues, velocity through the tissues. This is showing us the relationship between blood flow, velocity, and cross-sectional area in various blood vessels of systemic circulation. So we see the velocity of blood, and this kind of makes sense. Hopefully it makes sense. How fast things are moving through the system. The fastest is going to be what? Well, where's blood moving the fastest? Yeah, when it first gets pumped out of the heart, the aorta, the arteries, and the arterioles, we start to see a really big dive in how fast blood moves through the system. Where's the slowest moving blood? Capillaries. Yes? Why do you think that's the case? Imagine you had to get your lunch on a moving conveyor belt. Whoosh, whoosh. It's not going to stop. All right? So you have to grab what you need from everything that's moving by. If it was moving really, really fast, forget it. You're not going to be able to grab what you need, or you're not going to be able to maybe put stuff back. But if I slow that conveyor belt down, then you can grab what you want, and you can put your dirty dishes back on the conveyor belt, and everybody's happy, right? That's velocity is different than pressure, okay? Pressure in the system is at the lowest here in the vena cava. But things are moving still. Why are things moving still? If the pressure's so low, how can they move? Right. Muscles are helping push them, but remember, everybody's pushing from behind. So we still move, but the pressure might not be as high. Does that make sense? Kind of, sort of, maybe? The total area, how much we have there in the beds, is going to increase quite a bit in the capillary region. Look at all those branches, and what was that thing that I had, a branch off of a major vessel to feed a bunch of areas, began with an A. We talked about it last class. Anybody? Nobody? Anastomosis. Very good. So think of all those branches. And that's where we're going to see the total area the most in the capillary beds. And that makes sense. We've got to feed who? Who are we feeding? Everybody. Every single cell in your body needs to have some way to access nutrients and waste. So we see that relationship with respect to velocity and area. So, autoregulation, local regulation of blood flow. Oh, another exciting diagram. Some of the different metabolic controls, chemical changes, hormonal changes. This diagram is a summary of intrinsic and extrinsic controls of arterial smooth muscle in the systemic circulation. Now, if I can control the smooth muscle, and this is what we're going to find in the tunics of these vessels, control the contractility of them, I'm going to control what? If I constrict the vessels versus not constrict them so much, that's going to control pressure in the system and how fast or slow everything moves through the system. So this diagram is nice because it tells us some of the different players in controlling blood vessel diameter. There's intrinsic mechanisms inside the body, or auto-regulation. And when we talked about the autonomic nervous system, we were talking about things that sort of happened, what? automatically based on information that is being received at the central nervous system point. So the amounts of different things can either cause blood vessel dilation or blood vessel constriction, depending on what has to happen with pressure in the system. So if the pH gets messed up, it might cause what? Blood vessel dilation. Oxygen. Amounts of, decreased amounts of these guys. So when pH starts to go down, I make more acid. When I make more acid, it's because I have too much carbon dioxide in the system. So if I have too much carbon dioxide, I don't have enough what in the system? Oxygen in the system. So the levels of carbon dioxide and oxygen also have an effect on your blood's pH. If I have increased amounts of carbon dioxide, again, I don't have enough what? Oxygen. Increased amounts of potassium, prostaglandins, adenosine, I know that. Heard that. Adenosine, triphosphate. If I have lots of loose adenosine, I've used up maybe too much ATP. Have to make more. Another gas that can also, believe it or not, control blood vessel diameter is nitric oxide. The endothelial cells themselves can pick up signals and cause blood vessels to constrict. So myogenic controls refer to what? Myo, muscle. So when I feel a stretch, I can constrict. Nerves, sympathetic, parasympathetic, epinephrine, norepinephrine can also have an effect on blood vessel diameter. So the sympathetic nervous system, what's that do for a living? Speed things up. So when we're talking about speeding things up through these blood vessels, what can the sympathetic nervous system do real quick? Constrict. With the help of some hormones, we have epinephrine that can cause constriction. Norepinephrine, going to do the opposite. Remember our wonderful little hormones in the Renin-Angiotensin Pathway when we had to increase pressure in the system? They can also play a role in vasoconstriction as well. And then atrial natriuretic peptide. Who the heck makes that? The heart. And if I'm going to dilate a blood vessel, what might that be released when? What happens? If I make a blood vessel big, what am I going to do to pressure in the system? Decrease it. So when blood pressure goes up, ANP released by the heart, and in that same region as those baroreceptors are, yes, are going to help regulate pressure in the system. When pressure goes up, that hormone is going to cause vasodilation. Yes? So the diagrams in this, again, if you can talk your way through them, it'll give you a much better understanding. So extrinsic mechanisms are going to help maintain mean arterial pressure and redistribute blood during exercise and thermoregulation. All right. Blood flow to special areas. Why is this here? I don't know. All right. They talk about blood flow to skeletal muscle, which is important. Some of the different hormones, again, in that chart. Epinephrine is going to help with blood flow. Norepinephrine. Blood flow to the brain, about 750 milliliters per minute. And why do you think blood flow to the brain is extremely important? delivery of nutrients, get rid of the wastes right away. We don't want them building up in the brain, and most importantly, that oxygen to help with the whole process. The skin, important for temperature regulation, and also I have to supply nutrients to the cell. So there's a blood reservoir in the skin. The lungs, why do I need to bring blood to the lungs? Yeah, that's where my oxygen exchange is going to take place. That's one of the vital things that blood is going to help transport through the system. So lungs and blood flow is very important. And of course the heart, hello, that's the big pump. So blood flow through the capillaries and capillary dynamics. This diagram here helps us with what's going on in the capillaries as far as transport mechanisms go. So there are 4 possible ways that things can get from blood out into the tissues and opposite. And this diagram shows us some of those different mechanisms. So we can get blood through the tubes and movement of nutrients and wastes through simple diffusion. Remember what diffusion was? What? Correct. Movement with the concentration gradient, movement of a high concentration to a low concentration. So some things will move just on the principles of simple diffusion, from a high concentration to a low concentration through a membrane. And usually it's lipid-soluble substances that can do this really easily. Why? Lipid-soluble Yeah, cell membranes are what? They're phospholipid bilayers, right? Now we also need some movement to happen, or some movement can happen through the spaces between one cell and another. So movement through the intercellular clefts. And water-soluble things can move fairly easily through those spaces. What else? Some of our capillaries have windows or fenestrations, and the things can move in and out through those windows. And then sometimes the cell itself can be very selective and grab things from the plasma and pull them through to the other side. Through endocytosis and exocytosis, we can transport via those little packages or vesicles through the cell. And here's another scary one. So the next part of the book talks about some of the different pressures that are going to affect movement in the capillary beds. One of them is hydrostatic pressure. Hydrostatic. Yeah, water pressure. Remember osmosis? Why did that get its own special little name? Osmosis was what? The diffusion of water. And the concentration of water in the system is going to affect passage of nutrients and wastes in the system because of the pressure, hydrostatic pressure, it builds up in the system as well. So due to fluid pressing against the walls or pushing against the walls, we're going to have movement just due to pressure from water in the system. Now things are always want to go from a high pressure to a low pressure. Yes? Think of yourself. Do you want to be stressed out to the max, have 5 million things to do, or would you rather sit on the beach and drink a pina colada? I'm on the beach with the pina colada. Yes? High pressure, low pressure. And molecules will do that, follow a pressure gradient naturally as they move through the system as well. So they're going to go from a high pressure to a low pressure. And what we have to set up in the system is what we call pressure gradients. So it's very important to maintain a proper pressure inside those blood vessels, because when the pressure inside the blood vessels becomes too great, we don't have a big pressure difference between what's inside the blood vessels and what's outside the blood vessels. Make sense? And what's gonna cause me to move out if there's not a lower pressure on the other side? Nothing. I'm not going there, right? Because I want to go from a what? From a molecule, I want to go from a high pressure to a low pressure. So this section of the book talks about some of the different factors that set up these pressure gradients. Hydrostatic water pressure and osmotic pressure are going to help with exchange in the capillary beds. So this is a blow up of the capillary beds. Remember those arterioles fed into the capillary beds. And we look at the pressure gradient that's set up in the capillary beds. So when we have a net pressure of 35 millimeters of mercury and an opposing pressure of 25 millimeters of mercury from what's surrounding these capillaries, where does the stuff in the capillaries want to go? From a high pressure to a low pressure. So the net filtration pressure is 10 millimeters of mercury. Fluid moves out. When we get on the other end, again, we see that fluid may move what? In, because of difference that is negative in net filtration pressure. Why do I need to move stuff into the capillary beds at this point? What's the stuff? Waste products. Waste respiratory gases. When we hit the respiratory system, we're going to see this again, except they're going to be talking about the partial pressures of the gases that we're talking about. The pressures that are being exerted by the gases in our environment. So we have to have a difference in pressure gradient in order to move oxygen out of the capillary beds and into the tissues, and in order to move carbon dioxide from the tissues into the capillary beds. They have to go from what? High pressure to low pressure. Okay? So, this is basically the end of the chapter, believe it or not. I know that you want to memorize all of the different blood vessels. I know that you're really upset that I'm not making you do that, but this is pretty much the end of the line for this chapter. So this diagram is the events and signs of compensated, non-progressive hypovolemic shock. This is the end of the chapter. So we'll finish up the last page. Guess what you're having on Tuesday? Huh? Nope. The only thing you have to know about part 3, and I'll give you fair warning, on your next lab practical exam, guess which 2 diagrams? Well, actually this one. I think it's just arteries. Yeah, everything. This diagram will be on your lab practical exam. Yes? So you're having a quiz on Tuesday of next week on chapter 19 to this point. So we're going to end here on page 720. Okay? And we will pick up with chapter 20 on Tuesday. Adios.